Okay, and we'll do the 90-degree thing.
Hey, welcome back, everybody. We're here for uh, we're going to see a proof of the Sagan-Swanson basis. Okay, go ahead, Brendan.
All right. Thank you. Thank you very much, Jim. So thank you all for coming. Today's talk is going to move to the second in this series of three papers that we're talking about. It's joint with three, well, at the time, grad students at the University of Minnesota. Robert Angaroni, Patty Cummins, and Trevor Karn, Satoshi Murai at the University of Waseda, and I was an author on this as well. So let's just kind of recall some ideas from last time and also some ideas from Andy's talks. So if J is a subset of the integers between 1 and n, we have this polynomial f sub j living inside S, and f sub j has a factor for each element little j of j, and it looks like x little j times the product of all of these subsequent differences, x little j minus x little k. And well, one reason why this polynomial is relevant is it gives us this kind of basis transfer result. So suppose that for all subsets j of the integers between 1 and n, we can find a set bj of polynomials, and we're going to let B be this kind of set of superspace elements obtained by taking a disjoint union over all j of bj times theta j. So if you can solve these 2 to the n problems in commutative algebra, if you can show that each bj descends to a vector space basis of S modulo this colon ideal, I colon fj, where I is the classical covariant ideal, well then B itself descends to a basis of the superspace covariant ring. And well, there was one referee that characterized this as ad hoc, but I hope I've convinced you guys that it's not totally ad hoc. This really was kind of using Grosvenor theory, at a very high level at least, with respect to the theta variables. Okay, so we're kind of trading a problem in supercommutative algebra for a problem in commutative algebra, but how do we kind of solve this problem? So one more recollection here. The Hilbert series of S modulo this colon ideal is a product of, well, J staircase Q numbers, right? So if n is 7 and J is 2, 4, 5, this is the corresponding J staircase. So the student was held back in grades 2, 4, and 5. It looks like this. And our goal for today is to prove, well, the following conjecture of Sagan and Swanson, right? So what did they conjecture? We're going to let MJ be really a very natural set of monomials, which by construction has this as its degree generating function. It's going to be the set of monomials whose exponent sequences fit under the J staircase. And I'll let M be the disjoint union over all J of mj times theta j, and we're going to show that M descends to a vector space basis of SR. And we're going to do this with the basis transfer principle. So we're actually going to show that these MJs descend to bases of these colon ideals, but we actually already know the Hilbert series of these colon ideals. And by construction, the degree generating function here matches the Hilbert series. So we just have to show linear independence or spanning. And as it turns out, we're going to show linear independence. But I'll say right away, we don't have an elementary proof of linear independence or spanning. So this will absolutely not be using Grosvenor theory. We're going to be using ideas from hyperplane arrangements. So open problem, find an elementary proof. So let's just kind of recall some ideas from Andy's talks. So A is going to be an arrangement, a linear finite arrangement of hyperplanes in C to the n. And S is our, well, polynomial ring, of course, but we're going to think of it sometimes a little geometrically as polynomial functions from C to the n to C. And we've got derivations of S, which can be thought of in an algebraic way as a free S module of rank n generated by partial 1, partial 2 up through partial n. But often I like to think about this as polynomial vector fields in C to the n. So partial 1, partial 2, partial 3 are like I hat, j hat, k hat, and so on. And living inside the derivation module of S is the derivation module of A. And well, this is kind of the algebraic way of looking at it. It's those polynomial derivations for which whenever you plug in a linear form for a hyperplane in A, you get something which is divisible by that linear form. So I always found this definition very hard to parse, but this is a little friendlier for me. These are the vector fields parallel to the hyperplanes of A. So if you look at the little arrow pointing out of a point in the hyperplane, that little arrow stays in that hyperplane. And the derivation module of A is a S submodule of the derivation module of S, and the arrangement is free if this is a free S module. And our kind of first example of a free arrangement is the braid arrangement. So here I've drawn it kind of as a positive root pose set for n equal 4. And this is a free arrangement. And here is a choice of basis for the derivation module, these kind of power sum looking things. And one little bit of terminology. So if you have a free arrangement A, it can be arranged so that a basis of the derivation module is homogeneous. And the exponent sequence, the exponents of A, they're just the multiset of polynomial degrees of elements of any basis. Those are uniquely determined. So for example, the exponents of the braid arrangement are, well, 0, 1, 2, up through n minus 1. Okay, so just a little bit of review there, and now I'll kind of pause. Questions? All right, so what's the new ingredient going to be? So I'm going to let A be an arrangement in C to the n, and I'm going to let deriv A be the derivation module of A. This is a submodule of polynomial derivations, which are a direct sum as I goes from 1 to n of S partial I. And I'm going to define, well, with one additional piece of data, something called the Solomon-Terao algebra associated to A. And this definition, it's a slight generalization of something introduced by Abe. This is Takuro Abe. Maeno, Murai, and Numata. So here's how it goes. I'm going to let D be a non-negative integer, and I'm going to choose polynomials C of partial 1, C of partial 2, up through C of partial n, that's my attempt at a math frac C, which are homogeneous of degree D. So I'm going to let C from dir S to S be the S module homomorphism that sends partial I to C of partial I. And this is defined for the same reason that you can define a linear map out of a vector space by specifying its value on a basis. Nothing else going on there. So the, do it in red, Solomon-Terao ideal is C sub A, and this is by definition, oops, the image of C on deriv A, and this is something that lives inside S. And because Derive is an S submodule. This is actually an ideal, and it is in fact a graded ideal in S. And we'll be interested in not just the ideal, but the corresponding quotient ring, and this is called the Solomon-Terau algebra. And this will be uh, ST for Solomon-Terau, AC, and this is S modulo CA. So just to be clear, this is a graded quotient of the polynomial ring. So we have the Solomon-Terau ideal and the Solomon-Terau algebra. And I think the first thing I have to do is actually show you examples to show that you've seen these before. So for my first example, we're going to look at the case of the braid arrangement. And we also have to think about homomorphism from dir S to S. And the homomorphisms that show up in this theory, at least so far, are not enormously complicated. This is actually a pretty important one. It just sends partial I to xi, right? Perfectly valid. You get a homomorphism from that, no problem. So the derivation module of the braid arrangement has basis given by x1 to the k minus 1, partial 1, up through xn to the k minus 1, partial n, as k runs between 1 and n. And if I want to think about what the Solomon-Terau ideal is, well, I just apply A to everything in this basis, and I look at the ideal that gets generated, and what you see is that you get the n power sums, or the co-invariant ideal. So we've rediscovered the co-invariant ideal, and therefore the Solomon-Terau algebra of the braid arrangement with respect to this choice of homomorphism is the co-invariant ring, which we've been denoting R. So we get the co-invariant ring. That's good news. Now let's do something a little bit more interesting, and this will kind of speak to a question that Jim asked a couple sessions ago. So I'm going to let AI be an ideal subarrangement of the braid arrangement. So what do these things look like? I have my braid hyperplanes like this. And I'm going to look at an ideal in this positive root poset, and I am just going to throw out those hyperplanes that are not in my ideal. So it's a downclosed set of the positive root poset. And again, I'm going to take this same homomorphism, which sends partial I to xi. And it's a theorem of Abe, Horiguchi, Masuda, Murai, and Sato. That if I look at the Solomon-Terau algebra in this case, what I get is a presentation of something called the regular nilpotent Hessenberg variety of type A associated to the root ideal I. So, um, this theorem, if you look at the paper of Abe Horiguchi, Masuda Murai Sato called Hessenberg varieties and hyperplane arrangements, it is not stated in this language. It also applies to any crystallographic reflection group. But this was really one of the big motivating examples of these Solomon-Terao algebras. Okay, so what arrangements are we going to be looking at? So we'll be looking at something just a little bit bigger than the braid arrangement. So if I write B tilde, this is going to be the extended braid arrangement. And it's going to have, well, all the hyperplanes of B together with the coordinate hyperplanes xi equals 0 for I between 1 and n. And just like the braid arrangement itself, the extended braid arrangement really should be thought of as living in a poset. And the way we're going to want to do this poset is as follows. We're going to have 1, 1, 2, 2, 3, 3, 4, 2, uh, whoops, 1, 3, uh, 2, 4, 3, 1, 4, and 4. So we're essentially putting these new coordinate hyperplanes along this diagonal up here. So you can think about this too as the braid arrangement one up. So you would have like kind of a mythical 0, right? Kind of a 0th coordinate, but you've set the 0th coordinate to 0, essentially. Okay, so this is the extended braid arrangement, and maybe it's not so surprising because it's so similar to the original braid arrangement that B tilde is free, and a basis just looks a little different. So it's x1 to the k, partial 1, and so on, up through x into the k, partial n, where k is running between 1 and n. So the exponents are 1, 2, 3, 4 up through n, not 0, 1, 2, 3 up through n minus 1. And uh, what is our homomorphism going to be? It's something we'll call I. I don't even know how to attempt a math frac I. And I is actually even easier than A. So it sends every partial I to 1. So even simpler. And well, if you think about it, if I were to apply this very simple map to this basis, what I would get is the ideal generated by the power sums, i.e., the standard coinvariant ideal. And therefore, the Solomon-Terao algebra of the extended braid arrangement, right, with respect to I, is we've rediscovered the classical coinvariant ring. So maybe I'll pause here. And any questions kind of about the definition of a Solomon-Terao algebra? Okay. So we're going to be looking at subarrangements of the extended braid arrangement. And kind of here's our first really kind of non-trivial fact. So suppose A living inside B tilde is any free subarrangement. So we've got the extended braid arrangement, that's free, and we have some sub-arrangement, which is also free. I'm going to let F be, well, the product over those linear forms alpha H corresponding to hyperplanes that I threw away, right, from B tilde to get A. So we'll do that. Then the Solomon-Terao ideal of A is a colon ideal, namely the Solomon-Terao ideal of B tilde colon F. Or in other words, we just computed that this is I colon F, the classical invariant ideal. So we're getting colon ideals of the classical invariant ideal, and that's kind of what we want to shoot for, remember, with basis transfer. So I'm not going to prove this fact for you today. You can look at the paper, but I will kind of outline some of the big ideas in the proof. So the most important thing is this kind of miraculous lemma of commutative algebra that actually appeared in that Hessenberg varieties and hyperplane arrangements paper. That was kind of our first entry into hyperplane arrangements. It's this lemma that says, well, if I have these ideals that are complete intersections, under what circumstances can I assert an equality of colon ideals like this? Right? And this actually applies beautifully here, and you get to use some facts like, for example, the sum of the exponents in a free hyperplane arrangement is the number of hyperplanes in that arrangement. That actually ends up being quite relevant. And this applies in more generality than what I've written here. You also have to prove something about when this polynomial f is an element of the covariant ideal, and that has to do when this subarrangement A is essential. So there's kind of a lot of interesting algebra here, but I want to kind of get to maybe a little bit more of the combinatorics. And maybe some of this combinatorics might be, if you haven't seen this before, well, when is A free? I mean, I have this kind of mysterious freeness hypothesis, but how the heck do you decide if an arrangement like this is free? Well, here's what you do. So we have our extended hyperplanes like this. And I'm just going to pick, well, I'd be lying if I said it was random, but I will pick a subarrangement like that. So we have those four hyperplanes, and we're wondering if this is a free arrangement. So I have this arrangement A, and I'm going to construct a graph, which I'll call gamma, and this graph will be on the vertex set 0, 1, 2, 3, 4, 5 up through n, like that. And how am I going to build my graph? Well, whenever I see a hyperplane that I fill in, like this 1, 2, I'll put an edge in my graph, and 2, 3, and somehow like the coordinate hyperplanes have a mysterious 0, so I have a 0, 1 and a 0, 3. So I have this arrangement, which is a graph, and subgraphs of the complete graph on n plus 1 vertices correspond to subarrangements. And a result of Stanley states that A is free if and only if this subgraph gamma is something called chordal, which means no induced cycles of length bigger than 3. So this, for example, would not be free because of, well, this 4 cycle. And in fact, freeness and chordality in this particular context are equivalent to something stronger called supersolvability. Freeness is usually very, very hard. I don't want to give you the impression that it's easy, but for these kinds of arrangements, we have a nice combinatorial understanding. Okay, so this is a non-example. We can't apply this theorem here, but what will we be applying this theorem to? So this definition was a contribution of mine living in San Diego. So we're going to be looking at southwest. Subarrangements A of the extended braid arrangement. And I think that it would be best to define southwest subarrangements with an example. And here goes. So we're going to have n equals 6, actually. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 2, 1, 3, 2, 4, 3, 5, 4, 6, 3, 1, 4, 2, 5, 3, 6, 4, 1, 5, 2, 6, 5, 1, 6, 6. So we have this extended positive root post set. And the idea of a southwest arrangement is that you are closed under motion towards San Diego. You are closed under moving southwest. And what's one example? Well, I could do 1, 2, 3, 4, but not 5 and not 6. And then maybe I do 1, 2, but I kind of give up in this diagonal. I give up the ghost. And then maybe I have a full diagonal. That can happen. And maybe I have something like 3, 4, and 3, 5, but not 3, 6. And maybe I have 4, 5, but not 4, 6. And I have a not 5, 6. So every ideal arrangement is automatically southwest, but southwest arrangements don't have to be ideal arrangements like this. The number of southwest arrangements is like n plus 1 factorial. And to a southwest arrangement, I am going to associate a sequence, which I should probably not call the H vector. It is the H sequence, although I might accidentally call it the H vector. And the idea of the H sequence is that we look at these Seattle to Miami diagonals like this in our arrangement. Okay. And what we're going to do is just count up the numbers on these number of black dots in these diagonals. So here I get 1, 2, 2, 3, 3, and 1. So this is the H sequence of my southwest arrangement. And the fact is that every southwest arrangement is free. That's not terribly difficult to show with the Stanley criterion with exponents given by the H sequence. So, for example, this is a free arrangement with exponents 1, 2, 2, 3, 3, 1. By the way, why do we call the H sequence H? H is for Hessenberg. If I had an ideal arrangement, this would be cryptomorphic to something that we would usually call a Hessenberg vector. Okay, so we have these free arrangements. So questions at this point? All right, so what are we going to do with these free arrangements? Well, we'll do the following thing. We're going to apply really the one inductive tool that exists in the theory of hyperplane arrangements, namely deletion restriction. So if A is any arrangement, and H is a hyperplane in A, we can kind of get two simpler arrangements. So the first is the deletion, obtained by removing H from A, another arrangement in the original vector space. And the second is the restriction. And to define this, you look at the intersection of all the other hyperplanes in your arrangement, which are not the hyperplane you started off with the hyperplane in question. So this is an arrangement in a vector space of dimension one down. Okay, so let's state the following fact. So we're going to use this combinatorial gadgetry to build up something algebraic, namely short exact sequences. So I'm going to let A now be a subarrangement of the extended braid arrangement, and I'm going to let H be a hyperplane in A, and we're going to assume two things. The first is that A, the deletion, and the restriction are all free. So sometimes an arrangement, a deletion, and a restriction are called a triple. And we would say we have a free triple. And secondly, if I write down the exponents of A, I'm going to get some multiset. And I'm going to single out a certain element of my multiset, EK. And if I write the exponents of A with H removed, well, I have the same multiset, except now the value of EK is reduced by 1. And if I write down the exponents of A contracted, I have the same multiset, except now EK, or at least one copy of EK, is deleted altogether, right? And the value of K is going to be uniquely specified if all of these things are true. And I'm going to be a little bit, this is not standard terminology in Orlik-Tarau. I'll call these things good exponents. So I have a free triple with good exponents. And there's a famous theorem of Tarau that says that in the second condition, if any of these two statements about exponents are true, and if the two corresponding arrangements are free, then the third statement is true and the third arrangement is free. This is a deep thing called the addition theorem. So what are we going to do with this? So we have a short exact sequence of the following form. 0 goes to the Solomon-Tarau algebra of the deletion with respect to my boring derivation, my boring module homomorphism, sorry, I, which sends everything to 1, all the partials to 1. And this first map is multiplication by alpha h, that linear form, so it bumps up degree by 1. And then in the middle, I have this big Solomon-Tarau algebra of my whole arrangement. And over here, I have the Solomon-Tarau algebra of my restriction. And this goes to 0. And this last map, I'll just say, is a canonical projection, really. The coordinate ring of kind of a hyperplane is naturally a quotient of the coordinate ring of the corresponding space. So that's a degree 0 projection. Okay, so this is starting to look more promising, right? Because if I have inductively two bases of spaces that look like this might help me prove that a set of monomials here forms a basis. Now, again, I'm not going to entirely prove this. So this is something that holds true in a greater generality than what I've written here, but I'd like to kind of at least give you an idea of the proof. So let's not talk about Solomon-Terral algebras, this newer thing. Let's talk about derivation modules. So we always have an exact sequence of derivation modules 0 to derivation module of a deletion, multiplication by alpha h, derivation module of the whole thing, to a canonical projection onto derivation module of the restrictions, restriction of vector fields. And this isn't actually all that mysterious, right? So what's this first map? It's taking your vector field with I hat, j hat, k hat and multiplying by a non-zero linear form. And that's injective, right? Multiplying by a non-zero thing in the polynomial ring is injective. The composition of these two things, well, why is that zero? Well, if I multiply by alpha h, right, I'm basically saying that, oh, hey, my thing has to vanish on the hyperplane h, correct? And furthermore, why am I exact in the middle here? Well, this comes down to if I have a polynomial that vanishes on a hyperplane, it's divisible by the linear form corresponding to that hyperplane. So a little bit non-trivial, but kind of closely related to Neustadt-Zatz-like ideas. So we always have that SES, and or not short exact sequence yet. And if you're free, and if you have good exponents, that will imply the last map is onto. And this really is just comparing vector space dimensions, right? Because if I know that I'm a free module, and if I know what my exponents are, that's telling me the Hilbert series of these things. And if the Hilbert series of this plus Q basically times the Hilbert series of this adds up to the Hilbert series of this, and if I'm injective here, and if I'm exact in the middle, then I am forced to be a surjection. So this really is just kind of a statement of linear algebra when you kind of unwind things. And at this point, I'll just say apply I to pass from derivation modules to Solomon-Terral ideals and use uh, the fact that what um, if I look at, say, for any arrangement A, IA is equal to the covariant ideal colon um, product over H prime and B tilde mod A alpha H prime. So you use this kind of colon ideal property there. Okay, and again, you can look in the paper to see more details, but it really kind of comes from this classical geometric idea here. All right, so what does this all mean combinatorially? We want to delete and kind of contract with respect to certain hyperplanes. Well, let me flash back a slide and shamelessly copy paste. So we're going to copy this. We're going to paste it. And also we're going to shrink it. And so the hyperplanes that we're going to be deleting and contracting with respect to are all going to be coordinate hyperplanes. And we're going to be looking at this top coordinate hyperplane that appears in your arrangement. So we're really only going to be doing this deletion contraction when you have at least one coordinate hyperplane. And it kind of makes sense that you would look at that top hyperplane because, well, I want to stay southwest. And which coordinate hyperplane could I remove to say southwest? The top one. So let's take a look sorry. What happens when you delete this fellow up here? So if I delete you, well, this has the effect of reducing, right, the number in this fourth diagonal by ones. Like this 3 becomes a 2. So that's good news, kind of like good exponents. Now restriction is a little bit more interesting. So if I restrict, I better zoom in here. So I'm restricting to x4 equals 0. And the way that you do this is you take the equations of your hyperplanes and you plug in x4 equals 0 into each of these equations. And what this has the effect of doing combinatorially is pretty nifty. You perform, well, some kind of surgery on your positive root poset. So your positive root poset or extended positive root poset gets a little smaller. You draw this kind of V shape here. And, some of these hyperplanes that appeared in your arrangement, like, for example, this x24, well, he becomes an x2, but x2 was already there, right? Because I'm southwest. And X14, that was already there. X34, that was already there. So the things along this line, the southwest condition says that they were already in my arrangement. Now, you might have some things along this line, like say X45, that's along this line. So X45, if I say that X4 equals 0, X4 equals X5, that implies that X5 is 0. So I pick up, maybe I'll draw it in blue, this new hyperplane. So we had this kind of picture here where this hyperplane kind of got warped up here. And lo and behold, what we get is a southwest arrangement. And not only do we get a southwest arrangement, but what happens to the exponent sequence? Well, this fourth thing, yoink, it goes away. And because this warping procedure moved things within the same diagonal, everything else, right, inside the exponent sequence stayed the same. So if I delete and I contract with respect to this kind of maximal coordinate hyperplane, if it appears, I stay within the world of southwest arrangements, so I get free arrangements in my triple, and I have good exponent sequences. So we are pretty much in business. So the thing that I will say a little bit more about carefully is the following theorem. So I'm going to let A be a southwest arrangement with H sequence, Hessenberg sequence, H1A up through HNA. Then the Solomon-Terao algebra of A with respect to I has basis, linear basis this time. Come on. Given by, well, those monomials which fit under the H sequence. So this is starting to look very similar, right, to the Sagan-Swanson situation. And here is how the proof is going to go. So if A has no coordinate hyperplanes, then, well, H1 of A is actually going to be 0, right? Because I don't see that x1 equals 0. And well, I don't know of any monomials that aren't Laurent monomials that have negative exponents. So the set of monomials is empty. And this means that the content of this theorem is that the Solomon-Terral algebra of A had better be 0 in this case, but here's the thing, if I don't have any coordinate hyperplanes, this guy, partial 1, partial 2, plus partial n, that will be a derivation of A, right? Because it's good with respect to all the braid hyperplanes. So if I apply I to this, I get the number n, which is well known to be non-zero. And what that implies is that the Solomon-Terral ideal is the full polynomial ring. And if I take S mod S, what I get is 0. So I am good in that case. So else, let P be maximal so that XP equals 0, this hyperplane is in A. This is that critical hyperplane, that red dot. And I'll call this fellow, I don't know, maybe H naught. Then we have a short exact sequence because we have a free triple with good exponents from 0 to Solomon-Terral of A without H, I, to Solomon-Terral of A, I, to Solomon-Terral of A, I was calling it H naught, sorry, A contract H naught, I, to 0. And what are my maps? Well, they have to do with the linear form for H. So this first map is multiplication by XP. And the second map is induced by setting XP to 0. Now, inductively, by induction, say, in the number of hyperplanes, we get bases of the required form on either side. And if you think about the effect on H sequences that restriction and contraction with respect to this critical hyperplane has, exactness gives the correct basis in the middle. There we are. Okay. So some steps weren't quite there, but hopefully that was at least broadly believable. And now, well, what about Sagan-Swanson, right? I wanted to say something about I colon Fj. So here's kind of a corollary, which I'll also call a theorem, that we're going to let J be a subset of the integers between 1 and n. Then, what do I want to say? I want to say that the set of x1 to the a1, x2 to the a2, up to xn to the an, where ai is less than the ith thing in the J staircase, is or descends to a basis of S modulo I colon Fj. And by basis transfer, this implies the Sagan-Swanson basis of SR. So we're almost there. And how are we going to do this? So if I have J a subset of N, I'm just going to say that we get a southwest arrangement AJ. And once again, I will define things by example. And once again, I will shamelessly copy from stuff that I wrote down before. Here we copy and paste. And I suppose here n is equal to 6. Oops. And this is not AJ yet, but let's say that J was 2, 3, and 5, maybe. So the way that you define AJ is you include all coordinate hyperplanes. It's kind of always there. And if I see an entry that is not in J, I include all hyperplanes in the corresponding San Diego to Boston diagonal. And if I see an entry that is in J, I don't include any hyperplanes in that diagonal. So 2 is in J, no hyperplanes. 3 is in J, no hyperplanes. 4 is not in J, all the hyperplanes. And 5 is in J, no hyperplanes. Now, of course, this H vector is now wrong. I have to compute the H vector. And what we obtain is 1, 2, 2, 2, 3, 3. And just for fun, let's underline the positions indexed by J, and let's compute the J staircase. So this is the H vector, and this is the J staircase. Well, the J staircase says I start at 1, 1, 1, I can't go up yet, 2, 2, I can't go up yet, 3. And you'll notice that this is quite similar, except whenever I have a position indexed by J, the H vector is exactly 1 larger than the J staircase. And this will happen in general. So I'm going to let uh, maybe Fj tilde be a lot like Fj, except I don't have the factors corresponding to the coordinate hyperplanes. Product over J and J less than K, Xj minus Xk. So Fj, this element we really want, is like Fj tilde times product over J and J of Xj. And well, here's the thing. If you have a product of two polynomials like this, you get a map, actually an injection, of colon ideals. We'll call this phi, or colon ideal quotients, I'm sorry. And it's going to go from I colon Fj, that's the thing we really want, to S modulo I colon Fj tilde. And the map is multiplication by the product over J and J, X little j. This is just a general fact of commutative algebra. And well, here's the deal. So we were calling this fellow MJ. And MJ, the stuff that lives below the J staircase, if I multiply by the product of all variables indexed by J, well, the H vector, right, was exactly, very conveniently, 1 bigger in those positions. So MJ maps under phi to, well, a portion of a basis, and therefore a linearly independent subset of S modulo I colon Fj And therefore, well, if you map to a linearly independent subset, you had to be linearly independent. So MJ itself is linearly independent, not linearly dependent, sorry, linearly independent. And thereby, by the Hilbert series result, Hilbert series of this quotient, MJ is going to be a basis. And therefore, we have a basis of the superspace coinvariant ring, and that proves the Sagan-Swanson conjecture. Thank you so much, Bruce, for coming. I hope you liked it. And
It was
this
great.
basis, and what?
I said it was great.
Thank you. And this basis, and in fact, the MJ basis too, will be really helpful in understanding the Grosvenor theory, or sorry, not the module structure of this quotient ring. And I'll close with a little warning. So when Andy and I wrote our first paper, we saw this hyperplane arrangements in Hessenberg varieties paper. We saw this miraculous commutative algebra lemma, and we both thought Satoshi Murai almost certainly proved it. Satoshi and I are co-EICs at Algebraic Combinatorics, so I've interacted with him for a while. I sent him an email and I got a very short response back saying, I don't work with Superspace. So later on, I visited Tokyo and I explained kind of the similarities between what I had been doing with the Minnesota students and what he was doing and how things seemed to be tied in with hyperplane arrangements. And then, several months later, the next year, he was able to solve the problem. We wrote up a paper together with some other stuff in it too. And you want to get gifts to people when you arrive in Japan. And I made a gift for him. I made two versions because one version isn't as good. So he has the other one. So this says a super commutative algebraist. So and on the back you have a southwest arrangement. So thank you all very much.
Thank you. Okay. Any questions for Brendan?
Yeah, I had a question, as you might expect. First of all, lovely proof and very well explained. Josh and I had this more general conjecture for a basis for any complex reflection group of the type GM1N. Can this method be pushed through in that generality?
Oh yeah, so that's a really interesting question. So in joint work with Sutane Bhattacharya, we were able to prove that conjecture, prove your monomial basis
Excellent.
conjecture. But our technique was sort of like you take the type A result and you push it further. So we kind
Gotcha.
of assume the result in type A and push it further, but actually in type B, you can use this arrangements picture and you get a different basis for the superspace coinvariant ring.
Interesting.
So it's not a monomial basis and involves things like xi plus xj or xi minus xj, the type B hyperplanes. And this was solo work of my student Sutane Bhattacharya. So
And what happens for higher M then?
For higher M, what does the other basis look like? That
Exactly.
so we're not sure.
We're not sure. Okay.
Yeah, yeah.
Thanks a lot. It was great.
Welcome.
Okay, any other questions? All right, so we'll look forward to hearing more next week about the module structure.
Cool.
So make sure that the next week is on Thursday because Tuesday we don't have any IPAC.
Ah, okay.
Okay,
Good point.
Thursday. Thank you.
Thursday. All
Thanks.
right.
All
See you
right.
guys.
So
Bye.
long.
Bye.